And our next speaker is Dr. Jan Jakůbek, Chief Scientific Officer at Advacam. His talk is titled Imaging Modalities for Non-Destructive Testing Enabled by Photon Counting Detectors. Dr. Jakůbek is a physicist and imaging technology pioneer with hundreds of publication papers and a long history of innovation in X-ray detector design and applications. His contribution focuses to various applications of the photon counting technology in the field of X-ray, radiography, and especially for non-destructive testing. Dr. Jakůbek, the floor is yours.
Thank you. Thank you for introduction. So that means that I'm getting old, or what? So how to control this thing? Here. Okay, so I got inspired by Josef and I had to include also my old photo to my presentation. So in this case it is 1993 when I participated in some test beam in CERN, actually working with first like prototypes of those now called photon counting detectors. At that time we didn't call them like that, we called them just pixel detectors. You see. Okay, and 32 years later, so we are here, and then this technology has evolved. That time I was working with Institute of Technical and Experimental Physics here in Prague under CTU. Then we established Advacam, and some like spin-off projects were created, and there is a group of companies which are using this technology, and many are collaborators and partners and customers. So we are pretty happy that it finally found some application field. This is not like just purely scientific thing. Okay, so I'm here speaking for Advacam. We are doing detectors, photon counting detectors. You have seen some results which were measured with those detectors already in presentations of my colleagues. And the number of applications is really broad, so of course radiography and different modalities in radiography, but also others. So we have our detectors in space, monitoring space radiation there. We are using them also for some medical treatment monitoring, like this one which is shown there for head cancer treatment. It is in Heidelberg, which is very nice. The basic principle of photon counting detectors is described here. I think that most of you know it. So actually we have always, if I would find the right button to point it, some sensor actually which is basically semiconductor material. Ionization comes, the radiation comes, makes an ionization which is then taken by electric field, directed to the pixels. And in the readout chip, you know, so these are two chips. The first chip is sensor, the sensor chip is readout chip. We have a complete chain of electronics in processing the signal from each individual pixel for each individual event. So this is the big difference. Just to compare it with standard like analog detectors, which are very often called digital, but they are in principle analog, like CCDs, flat panels. In those, you would have, instead of all this chain of electronics, you would have just few transistors, like 3 or 5. Here in one pixel, we have 6,000 transistors, so it is pretty high integration. So if you imagine how many pixels we have, then it is more transistor than you would find in modern processors. And of course, then there is some chain of technological steps you have to do, starting from wafers, doing these interconnections, these bumps, integrating it with sensor. Now there is a sensor, and then we would have a functional unit. This we call it assembly, sensor plus readout chip. And the biggest problem for a long time was the small size of the sensitive area of such device. And with the years, we developed the technology of tiling to place many of those units next to each other to cover larger and even larger areas to be well usable for radiographic applications. So main features for our technology is like a high resolution of 55 microns per pixels, so these are square pixels. Since we have pretty complex electronics here, we don't only count how many photons came or how many particles came, but also we can measure their energy, so we can measure spectra per pixel, and we can measure also the time when the quantum of energy would come. I will later on show you some examples how to use it for radiography. And there are many other things. Since the information is present in digital form here, it is basically like a memory, then you have fast access to it, so you can read it quickly, you can have like continuous modes, you don't have to stop acquisition when you are reading out the previous frame, so just having here several registers, you would still continue counting while the other register would be read out. So there are many combinations of those things. I will not talk about these technical implementations, I will rather show some examples. We do some standard detectors, but here for this auditorium I'm showing some kind of exceptions. So we can do any like shapes, even some detectors with a hole in the middle. We did even some curved surfaces for some particular applications. We can do some multi-layer setups where the particles will go through all of them. We can make a long rows, thick sensors like those. So many different versions. Okay, but the main topic is X-ray radiography and modalities we can use with this technology. So the first big advantage of this photon counting principle is the dynamic range. So actually the information is present in digital form and we have a count number of photons. So there is nothing like 0.3 or 1.7. So there is either 0 or 1 or 2 and it can continue counting in fact forever. It is absolutely linear, so even after a long time, if there would be 1,000 photons, then half an hour nothing comes, and first next would come, you would have exactly 1,001. So actually, it continues linearity. And since actually the imaging noise, actually in such detectors, always passes on distribution, which is square root of number of events counted, and then just counting more and counting more, we can make this noise smaller and smaller. So we can achieve very high dynamic range, which allows us, Joseph already mentioned that, to see very tiny objects, in fact, on top of some thick structures. For example, this is the mouse body, you see bones, you see some soft tissue structures, and if you zoom in some region next to pelvis and backbone, here we saw such kind of like oriented structure, which is the hair fibers on the surface of the mouse. So you can see the one single hair fiber over the all thickness of the mouse. That's the first advantage, kind of like trivial. Next one, we can actually play with sensitivity to different energy bands. So we can set the thresholds, for the pulses we are analyzing in the pixels. That way we can sense the changes in the spectrum of X-rays when passing through some materials. And since this, let's say, the transmission spectrum depends very much on that material, that way we can distinguish different types of materials. So traditional X-ray imaging would give you just a grade of shades, while we can assign some colors to it, and we can clearly see the differences in composition. In some cases, you don't know whether some region is darker because it is just thicker, or it is darker because it is higher Z. We can see that. And as I said, this high dynamic range, it's really high, so it's signal-to-noise ratio can be in like orders of thousands. For example, this structure is carbon fiber reinforced plastics. One sheet of it, which is very often used as an input window for flat panel detectors. Maybe you saw it, this kind of dark surface, because it is considered to be transparent for X-rays, and it shouldn't actually cause any like change of contrast. And if we put it in front of our detector, we can nicely see all the like fibers and bubbles and different structures there. So it's like looking through like a dirty window and looking to the world outside. So here's just a few examples for this of these principles. This color imaging allows us to distinguish materials, as I said. Something very like common piece of PCB. If you do standard radiography, you can't see. This is some FPGA soldered using BGA technology. So there are some balls beneath, and you cannot see them actually looking, by eye. So you have to do radiography to check whether these balls are really there, whether they are present, and they are properly soldered. If you do standard radiography, you cannot distinguish actually these balls and the solder. And sometimes there are some capacitors, the blocking capacitors. If you do this spectral multi-channel imaging, here we used 3 channels. Then you can, I assigned virtual color yellow to solder, to tan basically, then we can just check that if the point is actually shown in yellow, then the solder is present. And you can distinguish it from like tantalum capacitors there and other structures there in the PCB. Some other things, as I said, this detector is digital. That means it is fast, so one can do really thousands of frames per second. Here, this video was taken at speed of 1,000 frames per second, because mouse heartbeat is pretty fast. So it's really like 11 hertz, so one could almost hear it. And using that high frame rate, we could nicely see different phases of the heartbeat, and you can see the change of the contrast, that the blood is pumped from this chamber to the lungs. So actually the contrast between lungs and this heart would reverse. One can do this kind of like electrocardiogram, but it is not electro, but it is like radiocardiogram. To see like blood moves from atrium to chamber and from chamber to lungs and back. Next advantage, or this is the same advantage just presented with different samples, the speed. So this is another application we were asked to do, to participate in a big project where the intention was to sort minerals according to content of certain specific ore types and to select actually pieces which would contain enough of this target material from pieces which are considered to be waste. Nowadays, everything goes to factory where it is grinded to powder, and then there is this flotation and chemical separation, basically producing this toxic waste plus this separated ore. If you would extract the clearly identified waste in advance, you would save energy, time, of course, amount of these toxic things produced, and on top of it, this waste material would be used for construction of roads or something, so it is not really turned into waste. So this thing, what you have seen, this scan is taken from continuous stream. It was 10 seconds, and during these 10 seconds we have seen 12 meters square scanned with a resolution of 55 microns. You see that the whole image is 500,000 pixels by 8,000 pixels roughly during these 10 seconds, but it runs continuously. And the speed of the belt is in this case 2 meters per second. So if I would come back to see it again, you see that basically the stones are just like jumping out of the belt, to this kind of tray, and there is a pneumatic set of pneumatic nozzles which would just plough or blow to certain selected pieces and blow it away to another tray. So that's how this sorting works. The same system can be operated in 2 energy bins. So we can have a colorless, we can separate some interesting regions, and based on amount of them we can say with certain probability how much of target material or target ore would be there. So that's the standard radiography, attenuation based. But there are also other modalities. I will show a few. One is X-ray imaging based on phase effects, which was already discussed or shown by Sasha Sheng. I have different method of extraction of that signal, just to show you what is the principle of that thing. I have performed very scientific experiment on my terrace, actually putting there is kind of glass vase or something with the water and some foam, on the surface, and there were a few droplets of water on the walls actually here. And if you put a projection plane behind, like a piece of paper, and you use sunlight, to make a radiography of that thing. So this is normal radiography we would see normally with X-rays. We start to see some things. First, actually, the question I always ask my students is why we see it, because all the light which comes in comes out. So there is nothing opaque, everything is transparent. The bubbles are transparent, the glass is transparent, water is transparent. Because the light would change the direction of light. That's why we see it. So, and we see different sections. So, I have highlighted few. So, behind of the foam, we see like darker region, which is dark field. So, that means that the light was scattered out, so it doesn't continue straight. So it goes to all the directions. Close to like edges, we see this kind of enhancements because the light would be like directed to another place, and you would have more light coming here. So the light which would normally fall here, it comes here. So that's the phase contrast. And we have also such kind of like speckles. So if there are some droplets of water on the wall, they basically work as a lenses. So if you put your projection plane to right distance, you start to see these very nice, like always like darker regions, and in the middle you would have very sharp and very bright spot. And all those methods can be used for imaging with X-rays as well. I will not speak long about that. And we all know that all these effects are also they depend on wavelengths. So actually, if we would shoot to it with white light, we would see some rainbow, close to the edges. The same thing works with X-rays, just the angles are smaller. So you have to increase the distance to see that. So these are the principles. So light or X-rays, instead of continuing straight, it would be deflected or reflected. So there will be certain loss lines. So there will be some like darker, like line surrounding the edges in the image. And then next to it, there will be some like brighter region. And since it depends on wavelengths, on energy, and we can measure the energy, so we can perform two measurements. This image shows it. This is thin polyethylene strip, and you see this kind of enhancement of edges, dark and white, dark and white. With one energy, this is shown in green here. The signal is bigger. With another energy, the signal is less, because the angle is different. But the attenuation is the same. So here it is recalculated to equivalent thickness to have it the same. So one can subtract these two images from each other, and you can get the signature of this phase contrast effects because the absorption is reduced. Okay, so that principle is used for speckle patterns. We performed a nice experiment with mouse lungs. Because lungs, what it is, you have this alveolar structure inside, so it's like small bubbles, and they exactly can act as like lenses. So actually behind of this alveoli, in certain distance for certain energy, you would start to see this like bright spike in the middle. You have to always find the right distance and select the right energy, and then you see it. If you don't do that, then actually all the energies would overlap and you would not see anything. And the result is this, if you find the right place, you suppress completely the anatomy of the lungs, so you don't see these tracheas, you don't see the other tissues, you see only concentration of alveoli, everything else disappears, which is a nice thing, so you can really focus to certain shape of objects and localize it. This works also for porosity, by the way, for some plastic materials and such materials. The laminations, they were also discussed here. Exactly the same principle I was showing for this edge enhancement can be used for that. We see laminations only when actually we can access the lamination in this tangential direction, so for flat samples it is difficult to do that. But luckily there are some structures which are like of this L shape. This is some thing from aerospace industry, and if we would vibrate with that, here in this this bended part, you start to have delaminated layers. So we perform the measurement, and really you see them nicely. So these are the laminated layers of laminate. Here the aspect ratio is very stretched in this direction. So this is 3 millimeters, while this is 30 millimeters. So it's just for display. So you start to see various features there. And there is some technique how to extract it using this approach that you have to take two images with two different thresholds, subtract them, and then you isolate the laminations. Everything else disappears. And of course, just by turning the object, you can make like a 3D visualization of the shape of this laminated plane. So that's this modality based on change of direction of X-rays. I would like to spend also some time showing you another approach when we would look at individual hits. Here we still integrate the signal in the pixels with some conditions. We set the condition that we would like to see only selected range of wavelengths or energies, but we can look at each of them individually and collect a list of all the events detected, all the photons detected, and then analyze them from such a long database. There is a certain family of chips called Tampixes, Tampix 3, Tampix 4, for example, and in every pixel we have ADC basically integrated. So every pixel can measure an energy spectrum. Just as an example, I show here European 152 with many peaks. So we really measure the spectrum of this incoming radiation. There are some like bonuses. Sometimes of radiation they are seen differently than just like being like single pixel hit only. So we can see tracks of muons, as Uwe said, or we can see this kind of like snowflakes, which are alpha particles from the radiant decay in the air. But this is very rare, you know. And you can select or separate them or identify them and suppress them. If you are interested only in X-rays, you would use just these dots there. And if you can do that, then you can use this detector very nicely, for example, for XRF imaging. So you take, again, a piece of PCB in this case, shoot through it with X-rays. X-rays would excite these materials, and they would start to emit characteristic fluorescences. And then you perform exactly this type of measurements, that every pixel records the spectrum, and then you can go through different channels of that spectrum, showing content of different materials according to their characteristic X-rays. So this is a PCB, this is painting, so there are some pigments, there is the XRF image of the same thing here, and I will show you also some applications for X-ray diffraction measurements. So I will maybe skip this slide. It's kind of like overview of everything, but not saying much. I will jump directly to this XRD stuff because this is connected very much with material structure analysis. And we are talking here about defectoscopy mostly, and material structure is a very important part of it. You know well that actually if we would have a Japanese sword, then it would probably be made differently than some piece of whatever metal like can, you know, so it has to have different crystalline structure. So to check it, people use this XRD setup, shooting to the sample with a collimated XRD beam. At certain angle, you would start to have this reflection, typical for specific crystalline lattice. And you perform a scan, changing this angle, and at the same time you would change the angle of the detector, and you record basically such a spectrum where here you have an angle, and here you have intensity of reflected beam. And you are looking for peaks here. You are trying to localize the specific angles where you see the reflections, which are typical for crystalline structures. But unfortunately, very often, you don't have only the XRD reflected beam, but you have also some scattered radiation coming out of the surface. There could be also fluorescence coming from the sample. That's pretty often. And this background actually, you know, unfortunately carries also some noise. So your peaks are, of course, seen on top of this noise. And to be able to separate them, you need to have high statistics. These our detectors, they have nice feature because they are spectral, so we can select certain energy band. And since we know that this X-ray tube, this is very often X-ray tube with copper target, and people are detecting fluorescence of copper, which is 8 electron volts. So we would like to select only 8 electron volts, which is this red peak here, and okay, alpha of copper. So if we do such a thing, then the background in this measurement drops by factor of 30. Then the SNR is improved by a factor of 9, and you start to see even peaks which are very difficult to be seen in the original measurement. So either you would have much higher sensitivity, or you can make much faster scan, so increase the speed of scan by factor of 10, in fact, which is, you know, reducing it from like half an hour to 3 minutes, which is pretty big. What I will show you on top of it is something which was difficult to do before, because this previous method used energy of 8 kiloelectron volts for measurements. So that means that you could analyze only the surfaces of the samples. You couldn't go to the volume. In some cases, if you are welding something, the volume is important, of course, much more than the surface. So to be able to do such a thing, you have to let the beam to go through volume of the sample, but it has to be energetic enough to penetrate it. Then actually it would be, of course, reflected from some grains, some crystals, and it would create this kind of images we have seen before. But normal detectors, which would not have this capability of spectral measurement per pixel, would see such a kind of like fog. They would not see any like rings, nothing where you can calculate the angles, and based on the angles, you would be able to judge what is the sample. Our detector can see that, so it can measure these energies. So for each energy channel, you would have specific image like this. Sum of all those gives you this kind of fog. And then actually you can recalculate all those measured diffractograms to like one common energy and sum them up and reconstruct back like full diffractogram of this sample. The beauty of that thing is that you can use polychromatic beam from X-ray tube. You don't have to go to synchrotron. Normally people would do it with synchrotrons, going up to like 100 kiloton volts energy. So you don't have to do that. And on top of it, since you use full spectrum which goes through, all these channels are used. You greatly enhance sensitivity and speed of that measurement. So Josef already shown this image where you have two pieces of stainless steel welded, and since actually both these pieces, there were, I think, the thickness is 2 millimeters in total, 1 millimeter each, and they were made by rolling. And if you do rolling, you would orient the grains inside of the sample, and then actually you would not get circle, because not all the angles would be happening with the same probability, but you would always get this kind of like maxima here. So one sheet was rolled in this direction and another one in this direction. So having them both welded like this, you have this kind of 4 peaks here. But if you go closer to the weld, where the area was heated up, and then it recrystallized again, but it recrystallized homogeneously. So this orientation, this texture disappeared completely, and we see that it is isotropically distributed again. So you basically lose certain material properties because of the welding. So that's something you can do and going across of the full thickness of the sample. There are many other examples. I will show just a very last one which we processed just recently. We said, okay, since it is very fast, we can do these measurements in really milliseconds. So because we use all the spectrum, so the duration of the measurements can be like a fraction of a second. So we can watch also some dynamic processes. We took this plate of steel, we put it to some setup, we heated it up to 750 degrees C, and we wanted to see recrystallization of this steel from martensite to austenite and back during the cooling. So here you see the sample. Here there is the setup. Sample is hidden inside. It was pretty complicated thing. There is X-ray tube with collimators. Detector is here behind. And during the heating, actually, at the beginning we saw such a pattern behind. Then actually the pattern have changed. If you would be careful enough, you would see that this kind of like secondary rings are not there. They are kind of blurred. And then if you cool it back, then it appears again. One can prepare very solid model for it, and here I am showing actually what happens. You know, this spectrum here. These are angles here and intensity. These are peaks, typical for martensite structure. Martensite is this one for low temperature, and there is always like blue line and red line. Actually, red line is the model, blue line is the reality, the measured reality. It fits perfectly, and actually, as you are heating it up, you start to see a big change. So now it dramatically have changed. So now actually like 95% of that already recrystallized to austenite. But we unfortunately switched off the heating too early, so it was still actually continuing this recrystallization. Then we switched that off, and it started to decay back to martensite, and we ended up with martensite again. And analyzing this data, so what you have seen, this is reality, we could really find the content of martensite and austenite with precision better than 1% across of the full thickness of the sample. So that was amazing for us to see that it was such precise, the measurement. So we are already pushing to stop. Okay, let me just show maybe last slide. I will skip everything. This principle actually, I have described that we are measuring the signal in each individual pixel allows us to do some improvements of quality. Very often it happens that our photon would hit kind of like point in the pixel which is close to the border of the pixel. And then part of the signal would be detected by neighbors. So instead of having like one pixel responding, we would have several. So we would have cluster. And such a cluster, each pixel in this cluster would give us amount, how much charge, how much signal for that one event is seen. And that means that for that single event, we have 4 numbers measured, and it allows us to calculate 4 another things. So for example, we can calculate precise hit position in X and Y with better precision than one pixel. So this would give us 2 numbers. And then we can calculate depth of interaction, and we can calculate the energy which was lost. Because actually, if we have a detector like this one, which is of certain thickness, if the detection occurs close to the surface, then the charge has to be transported down. You can have some charge losses during the transport. For cadmium chloride, it happens. With silicon, we don't see that. So actually, we can improve all those parameters we normally have. So position would be improved, depth would be determined, and energy would be improved. And just to show you the result, so this is the result. This is this IQI measure or standard, which was described by Uwe here. This is the first generation of that standard, which went down to 50 microns, and we distinguished those wires perfectly. And the second generation, it goes down to 20 microns. This is this pair of fibers, 17D17, and even those are recognized well. So actually, we still distinguish it. So that means that we cannot measure resolution of our detector with this standard. So the standard should be updated. So, and the effect is that, for example, these chips, it was shown here by Sasha, this tomography of integrated circuit or PCB. This is the same situation. There is also chip wire bonded, and if you don't have this feature, you see here it's just a cloud, but here you see distinctive bonding pads actually in the detector. There are many other things I don't have time to talk about, like gamma camera, improvements of spectra, backscattering I wanted to touch, but maybe I'm pushed already to stop. So maybe I will just show this slide. Beauty of backscattering is that actually even very small signal gives us already information. If we are doing standard radiography, we are basically measuring a loss of intensity. So we have to first know what is the intensity, we put there a sample, and we see that there is a difference. To see, you are basically subtracting these 2 big numbers with certain noises, and the noise accumulates. Here, if you are shooting to some object, actually, you shoot with this like beam, and you look what scatters back. If nothing scatters, that means that there is no material. If you have just one photon scattered, that means that there is a material. So there is such a simple measurement. So this is kind of thermal insulation for some concrete structure. So it is pretty known scenario. And of course, people are interested whether this hydro insulation in between is still really there. So we wanted to see this like polyethylene foil, like 200 micron thick. And you cannot access it actually from other side. You don't want to remove all those panels. You don't want to damage it. So you do this measurement, and you see the foil here inside, and you even see some kind of gap behind if there is. And if you would look carefully, you see that actually in this image there was some muon which came during the measurement time. So actually all those points, there are like single photons only. But already this thing is enough to see the structure. So we don't need to have many photons. We need just few. And then we have already usable signal. Many other things, corrosion and that thing, such a things. That's it.
Thank you very much, Dr. Jakůbek, for your insightful talk, and sorry for pressing you by standing here. Now we have still a few minutes for a discussion. So if there are any questions, we are ready. Yes.
So the detectors we have tested, you mentioned that are quite small. What is the perspective? How large can you do the detectors? And what substitution of classical DDAs do you have as a competition?
The largest we have done was this detector. We always name it according to like number of tiles. The largest was 10 by 10. That means like 15 by 15 centimeters. There was a picture somewhere in the beginning of the presentation. And but with the time, we realized that many people would optimize, let's say, the price and performance that way that they would prefer something asymmetric. Instead of having a square projection plane, they would rather have like a stripe, which can be then used for scanning. And the other case which I wanted to show was this thing, because here the conveyor belt was 40 centimeters in width. So this detector was 40 centimeters long, actually. Yeah? And here we don't have to have a large area in the other dimension, because everything moves through the sensitive area. So actually the length matters. So it was, the detector here actually was this 7,680 pixels by 256. You see, no problems actually, you don't see them. No. Actually, the truth is that actually the edge pixels are twice as large. So normal pixels within the matrix would be 55 microns, and pixels along of the edge are 110 microns in size.
Thank you very much. I see another question.
Coming to think of it, wouldn't it make sense to double the counter depth of the periphery pixels then?
For what?
To double the counter depth of the periphery pixels.
Yeah, but you know, the advantage is that there is a speed, you know, so actually you can read out the data very quickly and then sum them up in the computer memory. So you don't lose anything, you know. It's different from analog devices where you always have to perform ADC conversion, then save it in the computer, and then you perform an additional one. And the additional one can have different linearity, different offset, and this is problematic. Here it is not, so we just continue counting in the computer.
Okay, so on the transmission application you showed us, so each of the round images, the round signal, is according to each element, or what?
What do you mean?
The transmission XRD.
Transmission XRD. Yeah, transmission XRD. Okay, this stopped to work. What? What should I do? It doesn't do anything? Okay. Yeah, I was pretty quick there right now. So these were these speckles. And the laminations, these things. So how it works actually, it was shown actually here.
Yeah, this one.
So you see there's like grain, which are like monocrystals. Yeah, and each of them has certain random orientation, or people would like to believe that it is random. Sometimes it is not random. So if actually this orientation of the crystalline planes would obey this Bragg law, so the angle of incidence of this incoming beam would be equal, or would satisfy this condition actually, then we would get constructive interference, and then actually you would have very high intensity seen for that particular wavelength. Other wavelengths would not do anything. There would not be interference. So, and since you have all the wavelengths present, then also other crystals which would not have right angle would fulfill this condition for different wavelengths. So all of them would cast some reflection to some direction, but for different wavelengths. So for us it is very advantageous that we have polychromatic beam, because then some wavelength would satisfy the condition for each crystal. So that's how it works. And since the angle is given, but only like angle of deflection or reflection, then actually it can occur to all the, you know, in 3D for all the other angles. So it would typically draw kind of circle if the grain would be very fine and isotropically oriented.
And the source is
X-ray tube with polymeristic.
It's a normal X-ray tube.
For example, for this martensite-austenite transition, the collimator was 1/2 by 1/2 millimeter, pretty thick. It was nothing like special.
Okay, thank you.
Thank you very much. I think we have time for last 2 questions.
Yeah, very interesting talk. Thank you. I noticed that you use different power sources sometimes, and do each of these techniques, are they optimized for a particular source power, or does it?
Yes. Unfortunately, yes. This is like, let's say, bottleneck of this method, because this ADC actually in the pixel works only if the number of counts is low. So actually, one of these detectors we normally use, this Timex3, can give you up to like 40 million counts per chip. But in the chip, we have 65,000 of pixels. That means that every pixel can have up to 100 counts per second, which is not enough for normal radiography. Luckily, there is a new chip which is 32 times faster, so then it will be like 3,200. For nanofocus sources, it will be fine because they are of low intensity. For radiographic sources, for NDT, it is far from actually the intensity people would use. So still there is a long journey to make them faster. Yeah. So that's the bottleneck, that we cannot be very fast. That's why actually we use these detectors for these applications where the intensity is low, like backscattering, XRD, XRF, or attenuation if it is measured with isotopes, for example. If you have isotope, then it is not that powerful as X-ray tube, and you would benefit of spectroscopy because you can separate only a certain peak and you can suppress Compton or reconstruct it even. So these are the advantages of these detectors with the ADC. But counting would work normally. And all these detectors, they have always both modes. So if there is this ADC, then there is also mode which supports just counting.
Okay, thank you.
Thank you, and I saw another one.
In the phase contrast images, do you have used your spectral fencing? Because you always need some coherence, energy coherence.
Spatial coherence is necessary here, So we have to have a really microfocus or nanofocus source here. So spatial coherence is enough to see the
But the energy coherence.
Actually, if energy cuts are okay, So you see it even without any. Actually, like Sasha was showing, So there was no actually particular energy selection, for that. He was using like propagation-based separation of these phase effects. Or here I used like energy differences. That actually each energy would deflect differently, because it creates this like a rainbow thing. So, but you don't need any special.
If everybody is satisfied, we can move on next talk, and thank you, Dr. Jakůbek, for your inspiring talk.